Let's take a look at this section. And as a starter question, I've got some just some reminders about how we work with exponents and stuff like that, because this section is on exponential functions. We're going to be doing some graphing and some applying of exponential functions and those ideas. So if I have two bases that are the same and they've got different powers on them, what do I do when I multiply those together? Okay, I add the exponents. So this would be b to the m plus n. And that would be like having x squared times x to the third. That's going to be x to the fifth, right? If I have a power raised to a power, what do I do with those? So that would be like having x squared raised to the third. Multiply them together. So this would be x to the sixth, and this would be b to the m times n. Okay, one of the cool properties about exponents is they apply to whatever they're over, as long as it's a multiplication problem. So if I have a times b, and it's important that it's a times b, if it were a plus b, it wouldn't work like this. Okay, you can apply the exponent to each one of those factors separately. So this would be a to the n times b to the n. And an example of that would be, let's say I had x squared y cubed. Well, this would be x to the third, or sorry, x to the sixth, y to the third. Okay, so it applies to each one of those factors separately. And what does the negative in an exponent mean? Okay, it means move it down to the bottom, right? Okay, what it means is it means reciprocal. Okay, so there are actually three parts to an exponent: the sign of the exponent, positive or negative. Okay, sometimes we'll even have fractions for exponents. I think we reviewed a little bit of that in chapter P. So this means reciprocal. So this means 1 over b to the n. If I have a number raised to the 0 power, what's the answer? Answer is 1. And what if I have 1 raised to any power you want? Also 1. Okay? So, again, this section is on something called an exponential function. And exponential functions look like this. So I'd have f of x equals b raised to the x. So the base is a number, and the exponent is a variable. Base is a number, exponent is a variable. And we have a name for this. And if you'll call these, if you'll use the vocabulary that I'm using, I think in the long run it's going to make things easier to understand. It's also going to make the next couple of sections easier to understand. So this is called exponential base b. We name an exponent according to what the base is. Okay? And these come up a lot, and what I'd like to do is take just a second and look at these three functions right here, all of which have an x, all of which have a 3 in them, but they appear in different places. And because they appear in different places, they make completely different shapes. Okay, now this is a shape that we're familiar with. We've seen this before. Okay, if I have 3 times x, it's just the line 3x. It looks like this. It's got a slope of 3. If I plug in a 1, I get out a 3. If I plug in a 2, I get out a 6. Whatever number I plug in, all I do with it is I just times it by 3. If I have x raised to the third power, that makes a completely different shape. It makes this cubic shape. Looks like this. If I plug in a 1, I get out a 1. If I plug in a 2, I get out a 2 cubed. So the base is what's changing now, and the exponent is always 3, where here it was just 3 times whatever we plug in. So if I plug in a 2, I get an 8. If I plug in a 3, I get a 27. So I'm using whatever I plug in 3 times in a multiplication problem. Okay? And if I plug in a -2, I get out a -8. So these two shapes we've dealt with before. Okay, this one, even though it's got a 3 and an x in it, because they appear in different orders and in different places, it makes a completely different shape. Okay? So this shape, we're going to investigate right here. Okay? Now, when I plug a number in, that serves as the exponent on a base of 3. So let's talk about what happens right here. If I plug in a 0, so this would be 3 to the 0 power. 3 to the 0 power is 1. Okay? If I plug in a 1, 3 to the first, what's that? That's 3. Okay? What if I plugged in a 2? I get 3 squared, so that's going to be a 9. Okay. What if I plugged in a negative 1? So this would be 3 to the negative 1. What does the negative in the exponent mean? Reciprocal. So this would be 1/3. And if I did plug in a negative 2, what would I get? 3 to the negative 2. I get 1/9. So here's what happens when I graph this. So let me blow this up just a little bit. So I get negative 2 and 1/9. That's kind of a hard thing to graph, but we'd be about right there. Negative 1 and 1/3, so we'd be about right there. And 0, 1, so I'd be about right there. Now, even on this little bit of a graph right here, we can see that there's a little bit of a curve to this. Okay, and then watch what happens here. This would be 1, 3. That's a big curve. We've got a big bend going on in the graph right here. And if I plugged in a 2, I get a 9. So if I did a 9 would be way up here. So this is what that graph would look like. It would come down here. Okay. First of all, it continues to get larger and larger and larger. Okay. Hits this point, hits this point, hits this point. Now, what happens the further I go out here? What's that? The closer it gets to 0. Would it ever equal 0? It would never equal 0 because I'm never going to be able to take 3, which is a positive number, raise it to a power and get something that's negative. So this is just going to get smaller and smaller and smaller. So we're going to have a horizontal asymptote of y equals 0. Now, when we graph something like this, it's a good idea to graph 3 key points, and those 3 key points are right here. Okay, these middle ones that I had on here to begin with. So this one is negative 1, 1/3. This is 0, 1, and this is 1, 3. Those 3 points are important on an exponential function, just like a vertex is important on a parabola, because that's where the bend happens. Okay, it gets really steep. Okay, in fact, if you were to just look at this section of the graph, it kind of looks like just a steep line. And if you were to look at this part of the graph, it kind of looks like just a shallow line. Okay, but these 3 points right here kind of define where that bend happens, the big bend in this curve. Okay, so it's very flat out here, approaches the horizontal asymptote y equals 0, goes through negative 1, 1/3, 0, 1, 1/3, and it just gets steeper and steeper and steeper. Okay, any questions? Okay, so here's what the graph looks like. And these 3 shapes are completely different because of where the 3 occurs and where the variable occurs. Okay? And let's just talk for a second about if I plugged in a 10, what number do I get out of this one? I get 30, right? Relatively big number. If I plug in a 10 into this one, what do I get? I get 1,000. Pretty darn big number. What happens if I plug a 10 into this? Yeah, go ahead and somebody, if you've got your calculator, throw that into your calculator. So we get 30 on this one. So we go over 10, we go up 30. So let's think about this in terms of inches. If I went over 10 inches, I'd have to go up 30 inches to get to a point on the graph. If I went over 10 inches, I'd have to go up 1,000 inches to get to a point on the graph. On this one, go over 10 inches. Logan? What's the number? 59,049. So I'd have to go over 10 inches and I'd have to go up 59,049. Is that what it is? 59,049 inches to get there. Okay? Exponentials grow unbelievably fast. They are very fast growing functions. Okay? And they all have very similar shapes. So I want to take a look at this one again, and let's talk about what the domain and the range is. So if I were to look at this graph right here, what x values can I plug into this? If I squished it on the x-axis, what x values are covered? Yep, the whole thing in interval notation, negative infinity to infinity. What about the range? 0 to infinity. Okay? You can plug in anything you want, but you're only going to get out positive numbers because it's a positive base. Okay? If I graph this one right here, now there are 2 ways to do this. I'm going to show you how this textbook does this, and there are different ways of approaching this. The way we do this one right here is we think of this as a transformation. I'm going to change the x to a negative x. I change the x to a negative x. What I'm doing is I'm changing the x's on the positive side so they act like they're negative, and the x's that are negative so they act like they're positive. I'm doing a horizontal flip. I'm doing a reflection across the y-axis. Okay? So instead of running along this side over here and going up, this one's going to start up here and go down. So it's going to go through the point -1, 3. It's going to go through the point 0, 1, because that's on the y-axis. It wouldn't do a horizontal flip. It's right where it's supposed to be. Okay? And then we'd have this one right here. So it's going to do this. And again, we're going to have y equals 0 as a horizontal asymptote out on this end. And just to double check and make sure that we got this right, we did this via a transformation. We looked at that and said, okay, it's got the same base. It must have a similar shape to this. If I multiply the x by a negative, that's a horizontal flip. But let's check and make sure. If I plug in a -1, a 0, and a 1, let's see what we get here. If I plug in a -1, I get 3 to the -1. That'd be 3 to the first, so that'd be 3. If I plug in a 0, whoops, I get 3 to the 0, so that's going to be a 1. And if I plug in a 1, I get 3 to the -1. So that's going to be 1/3. So that is the right shape. Okay, what's the domain? All reals, so -infinity to infinity. And what type of answers do I get out? What's the range? 0 to infinity. Okay, any questions? Okay, so let's talk about these in general. So if you've got an exponential function, it's going to look something like this. Y equals b to the x. Okay, we call that, again, exponential base b. And there are 3 key points that we want to graph. And we always want to make sure that we get these right. It's going to be -1, 1 over b. Because when you plug in a negative in the exponent, it means reciprocal. That's why it's the reciprocal of the base. If you plug in a 0, it's always going to be 1. Any number to the 0 power is going to be 1. And then if I plug in a 1, it's whatever the base is. So it goes through -1, 1 over the base, 0, 1. Okay? Doesn't matter what the base is. It's always going to go through 0, 1. And then 1 comma whatever the base is. Again, that's called exponential base b. The base has to be a positive number other than 1. It would be a very boring graph if b was 1. Can anybody tell me what it would look like if b was equal to 1? What would it be, Noah? Yeah, it would always be 1. It wouldn't matter what you plugged in. The answer would always be 1. So it would be a very boring looking graph. The domain is always going to be all reals, -infinity to infinity. And the range is just going to be positives. Or sometimes you'll remember we call those non-negative numbers. You're going to get out positive answers, but no zeros or negatives. And it has a horizontal asymptote of y equals 0. Either over here on the left side or over here on the right side. Okay? Now, it's important to point out that what we're talking about there is just a plain old exponential, not a transformation of an exponential. But the cool thing about a transformation of an exponential is if you can graph this right here, you can figure out what this looks like based on the rules that we learned for dealing with transformations of functions. Okay? So, what would the plus k do to the graph? Yeah, so it's going to be up or down. It's going to depend on whether it's positive or negative, right? What's the h going to do? Left or right. So I'm going to put L or R. And I'm just going to put this little reminder right here that it does the opposite of what you'd think. So remember, if this is a +2, it's actually going to move it to the left 2. Okay? And this is going to be a vertical... What did we call these again? Okay, vertical stretch or shrink, and it can also vertically flip the graph. Okay, so we could flip it upside down. Any questions there? So just as a quick reminder of these, because this will come up again repeatedly throughout the year. Okay, in a couple chapters, we're going to be talking about trigonometry, and we're going to be doing some pretty cool looking graphs. Okay, if we understand these transformations now, we're going to be in much better shape in the long run, especially when we deal with functions like that. So let's take a look at this one right here. The parent graph for this one is what shape? for this guy right here. Radical x, a square root function, right? So it goes through, and I'm going to do this in black, it goes through 0, 0, 1, 1, and 4, 2. So this is what the parent graph looks like. But I need to take that graph and I need to do a couple things with it. Okay, I need to vertically stretch it, so I need all the points to be twice as tall as they used to be. So I need to be about that tall and about that tall. Okay, so there's the right shape right there. That's been vertically stretched, but what does the -1 do and what does the -3 do? What does the -1 do? Right 1 and down 3. So I'm going to go to the right 1 and I'm going to go down 3. So I'm going to have that point right there. So we're right here. And then I normally go over 1 and up the square root of 1. I'm going to go over 1 and up twice as far. So that's going to put me right here. I normally go over 4 and up 2. I'm going to go over 4 and up twice as far. So I'm going to go up 4. That's going to put me right here. So that's the shape we're after. We'd want to label these points 1, -3. Where would this one be? Two, -1. Because if I went to the right 1, that would put me at 2. And if I went up 2, that would put me at -1. And this one right here is going to be over 4. So that's going to be 5. And up 4 from -3, that's going to be 1. Okay, does this red graph, does it look like it's the original shape, vertically stretched, steeper than it used to be, and moved right 1 and down 3? Okay. Any questions there? Okay, let's take a look at this next one then. Same parent graph goes through these 3 points right there. That's the shape. What does the minus in front of the x do? Okay, this is a horizontal flip. This is a flip across the y-axis. So it's going to go from being over here to being over here. So that is what we're after. But what does this do? What does that negative in front do? That's a vertical flip. Flips it across the x-axis. So the one with the x flips it across the y-axis, a reflection across the y-axis. The one in front of it is a vertical flip, a flip across the x-axis. So it goes through these points right here. Does it look like it's been horizontally and vertically flipped? And could we name the points on this? 0, 0 doesn't change. -1, -1 doesn't change. And -4, -2. Sorry, -1, -1 does change. Both the signs there change. Okay? Any questions? Okay. I just need you to tune in for just a second. Watch this. It's always a good idea to double check and make sure that you're right. Normally, we can't plug negatives into radicals, right? But if I plug in a -4, watch what happens. What's the first thing we do with the -4? Change the sign. Negative times negative is positive. What's the square root of 4? 2 with the negative in front, -2. So that is the right graph. We got it right. Okay? So keep in mind those transformations, they come in really handy. We're going to use those repeatedly throughout the year. Okay, good reminder there? Okay, so let's take a look at these graphs right here. Okay, now we're going to graph each one of these and we're going to label the 3 key points where the bend happens, and we're also going to label the horizontal asymptote. Okay, remember, you've got it right up above. I'm going to write it here. It always goes through these 3 points. So I have 6 coordinates to figure out. It always goes through -1, 0, and 1, and that's a 1. So of the 6 numbers we need to figure out to graph this shape, we automatically know 4 of them. What does the negative, when I put it in the exponent, do? Negative means reciprocal, so that's going to be 1/4, and this is 4. So it's going to go through -1, 1/4, 0, 1, and 1, 4. So it's going to look something like this. Okay, if you could watch, please. If you've got the shape down, that's great. Let me just give you a little bit of advice. Something that people tend not to do here is they don't draw this in and label it. Remember, asymptotes help us get the right shape. So it needs to run along here and then hit these 3 points right there. What some people will do is this. Everybody watch, please. They'll make it look like this. And it will never get close to the x-axis that way. So if you draw in that horizontal asymptote, run along there, hit this point, hit this point, hit this point, put arrows on the end, and then label those 3 points, it's going to be very clear that you know exactly what you're doing. Any questions? Okay, let me show you 2 different ways to do this problem. This one looks like 2 to the x, but it's got a negative in front of the x. A negative on the x does a horizontal flip. So one way that you could do this is think 2 to the x. That would go through, whoops, -1, 0, and 1, and a 1. This would be 1/2, and this would be 2. So the parent graph, if you want to think of it this way, looks like this. What does the negative do to this? Horizontal flip, right? So it's going to take the stuff that was over here, flip it over here. That point's going to stay right where it is, and that's going to be 1/2. So the graph, instead of starting down here and going up, it's going to start up here, and it's going to go down. It's going to have a horizontal asymptote of y equals 0 over there, and this point would be -1, 2, 0, 1, and 1, 1/2. Any questions there? Okay. You don't need to write this down, you can just watch, but I do need everybody's attention because this is kind of an interesting application here. So if I were to do 2 to the -x, and I thought to myself, you know, Mr. Laws said it would always go through these points. -1, 1 over whatever the base is, 0, 1, and this is 1, whatever the base is. Okay, but that's only if it looks like this, not if it has a negative in front of it. So one thing we could do with something like this is we could say the negative in the exponent means reciprocal. Well, what if I thought of it this way? Reciprocal of 2 is 1/2, and then raise that to the x. Okay, I applied the negative to the base. That means it's a reciprocal, so this would be 1/2 to the x. Let's watch and see what happens here. This will go through -1, 0, and 1, and this is always a 1. If I plug in a negative, remember, it means the reciprocal of the base. What's the reciprocal of 1/2? 2. And if you plug in a 1, it's whatever the base is. Okay? Whatever the base is, you just put it right here. What's the base on this? 1/2. So it would go through the point -1, 2, 0, 1, and 1, 1/2. Okay. I like both of those approaches. This is nice from the aspect of practicing transformations, but this is also nice from the aspect that, guys, if you can make it look like a number raised to the x, it will always go through these 3 points right here, and that's where the critical stuff happens. That's where the big bend happens. Good there? Okay, let's take a look at this next one. You do have to be a little bit careful with this, and I don't think we ran into any of these when we were doing transformations before, but you do have to be a little bit careful. Here's how we need to think of this and how we need to write this. If you're going to figure out whether this moved to the left or the right, you have to have a factor with x plus or minus a number, a plain old x plus or minus a number. So in order to get this right, I've got to factor out the negative. So if I take out the negative, this is a -3. So this is a horizontal flip across, reflection across the y-axis. And which way does that move our graph? To the right 3. Right 3. So it's this shape right here, this one right here. I'll draw that again. 1/2, 1, and 2. It's this shape right here, but I need to horizontally flip it. So it needs to be this shape right here. just like this one right here, those 3 key points, and I need to move those 3 units to the right. If I move them 3 units to the right, which coordinate changes, the x or the y? The x does. So we're going to add 3 to each one of these. So this is going to move 1, 2, 3. So that's going to put us right here. This one's going to move 1, 2, 3. That's going to put us right here. And this one's going to move 1, 2, 3. That's going to put us right here. So I still have a horizontal asymptote. Run along there and hit these 3 points right there. I can label the asymptote as y equals 0. And I want to label each one of these points. This one is something comma 2. This is something comma 1. And this is something comma 1/2. What's this one right here? 2. What's this one? Hopefully pretty easy after this. Aren't we just going to the right one each time? So that's going to be 3, and that's going to be 4. If I took this point 1 comma 1/2 and I added 4 to the x coordinate, that would slide it to the, added 3, that would put me at 4 comma 1/2. Any questions? Okay, go ahead and flip the page over, and we've got a couple more that we want to graph. So I think we'll be able to finish these problems before we're done. So anything on the assignment where it just deals with just graphing, you could do those. Tomorrow we'll talk about the interest problems, because that's a really good application and something that I know for sure you'd see again in a college math class. So both of these are based on exponential base 2, and exponential base 2 goes through 1/2, 1, and 2. So they're both based off this right here. Let's do the red one first. What does the negative in front of that do? Vertical flip. It's a flip across the x-axis. So that's going to put my point here, here, and here. So that's going to run along the horizontal asymptote and hit these, hit these points right here. So it's going to look something like this. We'd want to label these. Again, if this point was 1 comma 2, a vertical flip only changes the y coordinate. So that's going to be 1 comma negative 2. If this point right here is 0, 1, a vertical flip only changes the y coordinate. So this is going to be 0, negative 1. And this one right here is going to be negative 1 comma negative 1/2. Let me label that up there. Okay. Okay, what does this one look like then? We take that same graph, and what does the negative with the x do? Horizontally flip this graph. So we've vertically flipped it already. That takes care of this guy right here. And then we need to horizontally flip it. So we need to take everything on the left, put it on the right, everything on the right, put it on the left. So I'm going to take this point right here, reflect it across the y-axis. That changes the x-coordinate. So this is negative 1 comma negative 2. Reflecting it on the x-axis doesn't change that one at all. And I put this point over here, so it looks something like this. And I'm not going to take the time to label all of those points, but that's what it would look like. Okay? So here's negative 2 to the x, and here's negative 2 to the negative x. Horizontal and a vertical flip on that one. Okay? Any questions? Okay, take a look at that next one. Take a good look at it. Okay, the parent graph is the same graph of exponential base 2. So it goes through here, here, and here. That's what the parent graph looks like. And then we want to figure out, what does that do? What does that do? And what does that do? Remember, if there's something with the x, it's got to be a positive x plus or minus some number. So I'm just going to put parentheses around that to remind me that that is factored. I have pulled out whatever the sign was in front of that. So I'm all set to go. What does this do? Reflection across the x-axis, that is a vertical flip. Vertical flip across the x-axis. What does the minus 1 do? It's with the x, right or left, it's going to be to the right 1. And what does the plus 2 do? Up 2, right? Okay, so I need to do a vertical flip of this shape. So if I vertically flip that, it's going to be down here, and down here. So this is the right shape. It's just not in the right place. And hopefully this point, and this point are pretty easy to figure out what they are. I need to take those 3 points and I need to move them. I need to move them to the right 1 unit and I need to move them up 2 units. So let's do them one at a time. I'm going to move this one to the right 1 and up 2. So that point would be 0, 3/2. This is at -1, -1/2 right now. Over 1 would put us at 0, and then up 2 is going to put us at -1/2 plus 2 would be 1.5. Everybody okay with that? Take this point and go to the right 1 and up 2. Puts us right there. 1, 1. This point right here is 1, -2. So if I go to the right 1 and up 2, that's going to put me right here. So I should be able to see what that is, or I can take this point, 1, -2, right 1, that would put me at 2, and up 2 from -1, or -2, that would put me at 0. Okay, now, just like I said before, this is where it's really critical. If the old horizontal asymptote was right here, if it used to be y equals 0, what is the horizontal asymptote now? It's going to be 2. So before you draw the rest of the shape, come right here and write y equals 2 is our horizontal asymptote. And then let's draw the graph. We need to run along here, right along that horizontal asymptote, and then I need to go through that point, and that point, and head off like that, put an arrow on both ends, and we're all set to go. Any questions? Okay, watch. Let's just double check. If we do a transformation correctly, we should be able to take a point on the graph that we found using the transformation, plug it in, and it should work. So let's plug in a 2. Watch what happens. I get -2, and then this is going to be 2 minus 1, and then this is going to be plus 2. So this is -2 raised to the first plus 2. Well, that's -2 plus 2, so what do we get? We get 0. Right graph, right point. We're all set to go. Any questions? Okay. Does anybody recognize this one? Anybody graphed this before? Okay. Does anybody know what number this is? Sven? Half a hand? No? What's that? It's part of a continuous compound interest formula. You're right. Anybody, so does nobody knows what this is called? What's that? Exponential base. Well, this letter is an E. Okay. Okay. E is the natural number. Okay. It's kind of like pi. It's an irrational number. Goes on forever, never repeats. Pi is the ratio of the diameter of a circle to its, the circumference to its diameter. Okay, it's a number that, I mean, we can't do anything about it. Pi is what it is. Okay, that's not going to change. E is called the natural number because it comes up a whole bunch in natural situations. It just naturally arises in developing different formulas and stuff like that. Okay, some areas are population growth, interest formulas, and different things like that. This is called the natural number. It is approximately, although not exactly, 2.71. That's roughly what it is. Most calculators have the exponential button on them. They have an E on them. You can type it in and it will give it to you out to 8 or 10 decimal places or something like that. Okay? But it's about 2.71. I think 2.7182 or something like that. Okay, so this is an exponential, just like any other exponential. Yes, it's weird that the base is this ugly number, 2.71 blah, blah, blah. Okay, but it works exactly the same. And the reason we study the exponential base e is because it comes up so often. In fact, if somebody says, I'm working with the exponential function, you don't have to ask them, well, are you doing base 2 or 3 or 1/2? What are you working with? If somebody says the exponential function, it is so important. This is the one they're talking about. They're talking about exponential base e. Okay? So, lock that away in your brain. Pi is 3.14159. E is 2.71 approximately. Okay? So, if I were to graph this, this goes through the same 3 points. We want to graph where the bend happens. It goes through -1, 0, and 1. This is a 1. This is 1 over e, and this is e. It has the same horizontal asymptote, y equals 0. So, 0, 1, no problem graphing that. 1, comma e. 1, comma e is over 1 and up about 2.7. So if I were to label this point, I just label it literally 1, comma e. It's even easier than writing 2.7. This is 0, comma 1. And this one right here would be -1, 1 over e. About -1 and then comma 1/3, roughly. Okay, it's a little bigger than 1/3. But as far as graphing goes, you can put it about that right there, about at 1/3. So that would be -1, comma 1 over e. So it runs along the horizontal asymptote, hits these 3 key points as it's starting to grow, and that's where the bend happens, and those are the 3 points that we'd label on that one. That is a very important graph. I would know how to graph it. If somebody says exponential base e, this picture with those 3 points should pop into your head. Okay? Again, e is 2.71, so we're a little closer to 3 than we are to 2 at that point there. Any questions? Okay, so let's graph these other two. Notice they're both based on exponential base e. What does the negative do to the graph? Horizontal flip. And what does this do? Move it up 1. So instead of going through -1, 1 over e, 0, 1, and 1, comma e, instead of hitting these 3 points, we're going to do a horizontal flip. So that point right there, that point right there, and that point right there. And then I'm going to take that graph, and I'm going to take every one of those points, and what am I going to do with them? Up 1. So I'm going to go up 1 right here. I'm going to go up 1 right here, and up 1 right here. What else am I going to draw before I draw the graph? Horizontal asymptote. Where was it over here? It was at 0, so I move it up 1, so I have a horizontal asymptote of y equals 1. There's our horizontal asymptote. So the graph does this. Does it look the same, just bumped up 1 unit? Hopefully. I'd like you to label those 3 points right there. -1, 0, and 1. All we did was move it up. Okay, here's the cool thing about this. This might seem a little bit overwhelming, but if this point right here is -1, comma e, which coordinate changes, the x or the y? The y does. By how much? So you literally write this down. This is even easier than doing the arithmetic for it. Okay, it's e plus 1. That is the point. This one right here would be 2. This one right here would be 1 over e, and I just added 1 to it, so it's 1 over e plus 1. So all you have to say here is, look, I know I'm supposed to add 1 to it, but these are pretty ugly numbers, so there it is. And that is the exact answer. Okay? And if you were to put in a -1, that is the exact number that you'd get out. Okay? Any questions? Okay, let's do this last one and then we'll be done. What's the base of this exponential? 1/3, right? Have I transformed this in any way? Do I have any flips? Have I slid it left, right, up, down, or anything like that? Nope. So the 3 points that it's going to go through are -1, 0, and 1. That's a 1. What does the negative mean again? If I plug it in and it's in the exponent? Reciprocal. What's the reciprocal of the base? 3. If I plug in a 1, I get whatever the base is. So those are those same 3 points, -1, 1 over the base, 0, 1, and 1 comma whatever the base is. So this is -1, 3, 0, 1, and 1, 1/3. Draw in the horizontal asymptote, y equals 0, runs along here, and hits those 3 points on its way up or down, however you want to think about it. Okay, any questions? Okay, you can do any of the graphing problems, all right? Okay, did I get all the tests back?